Hello everyone, I'm Zibo Wang from Nanjing University. It's my honor to be here to present our work, Accelerating Model Training on Ascend Chips, an industrial system for profiling, analysis, and optimization. This is a joint effort from Nanjing University, Peng Laboratory, Huawei, Shandong University, and Peking University. My presentation will cover the instruction, insights, system design, case study, and the conclusion. And first, I will introduce the background. As we all know, modern model training is incredibly complex. It involves a diverse ecosystem of hardware, models, software stacks, and various optimization libraries. Different roles are involved in this complex process, including developer, deployer, and maintainers, and they each have different goals. First, developer must identify specific bottlenecks that limit chain efficiency, and then design target optimization to mitigate them. Next, deployer must analyze the bottleneck and select appropriate optimization for varying models and hardware to achieve expected training performance. Finally, the maintainer is responsible for monitoring real-time training, capturing random and unpredictable performance fluctuations, and identifying the underlying causes. To achieve efficient training, we need tools that help us with three main goals: identifying bottlenecks, selecting the right optimization, and monitoring performance in real time. However, existing approaches fall short. They often suffer from three key problems. First, high profiling overhead. Fine-grained or continuous profiling is often too expensive for production environment. Second, partial bottleneck analysis. Many tools only focus on one specific area, like I/O communication, failing to provide a comprehensive system-wide view. Third, limited optimization scope. The few existing optimization tools are only effective in limited environments. These issues are prevalent in training practices on Ascend chips, and therefore users urgently need a systematic solution to alleviate training bottlenecks. Then I will describe the insights from our extensive practice. To build a better solution, we should first learn the background of Ascend chips, especially the similarity and differences with NVIDIA GPUs. As the left figure illustrates, both platforms share a common hierarchical training paradigm. Because of this similarity, many performance bottlenecks, such as those in parallelism, I/O, computation, and communication, are fundamentally hardware agnostic. However, their underlying chips architecture are quite different, and this introduces hardware-specific bottlenecks. A key example on the Ascend NPU is the AI CPU. This is a specialized compute unit for handling non-matrix computational tasks, and if not managed properly, it can create unique computation bottlenecks not found on other platforms. Our experience analyzing numerous production cases lead us to a key insight, is that the training pipeline operates hierarchically. Performance bottlenecks can occur either within individual operators tied to specific hardware like DRAM, CPU, NPU, and network, or between operators due to poor parallelism. Therefore, we propose a two-level hierarchical analysis. We first analyze inter-operator parallelism and then diagnose intra-operator bottlenecks. Here I will show our system design. Based on the insights mentioned before, we designed Hermes, a system-guided optimization of deep learning model training on Ascend NPUs. The workflow has three main stages: profiling, analysis, and optimization. For profiling, we use a cost-to-fine approach, starting with a lightweight monitor and then perform fine-grained profiling for problematic steps or devices. In the analysis, we employ a hierarchical bottleneck analysis framework covering parallel, I/O, CPU, computation, and communication bottlenecks. Finally, for optimization, we propose an optimization tool MSTT advisor, which automatically provides suggestions through bottleneck cost and optimization matching. First, let me describe the profiler in detail. To balance detail and overhead, Hermes used a cost-to-find profiling mechanism. It starts with a lightweight monitor to detect performance fluctuations. Once a slowdown is detected, fine-grained profiling is dynamically activated only for problematic areas. Gathering detailed data without interrupting training, combined with efficient parsing, the overhead of our profiling process is very low. Then let me introduce our two-level hierarchical analysis. It starts with inter-operator analysis. We analyze overlaps between computation, communication, and host operators using multi-component parallel analysis. If overlaps are poor, we're identifying parallel bottlenecks. Then critical path analysis helps us to pinpoint the most time-consuming operators on the critical path, guiding where to focus optimization efforts. For I/O analysis, we use a queue-based approach to analyze data pipeline you can see on the slide. We simply monitor the data, host, and the device queues to find the slowest step. For example, if the device queue is often empty, the MPU is waiting. Checking the upstream queries then tell us if the bottleneck is data fetching, processing, or reading. Our CPU analysis investigates why the MPU is idle, waiting for the CPU. The causes are diverse. They can be framework-related, such as operator comprehension and dispatch. They can also be system-level issues, like garbage collection, resource contention, or environment misconfigurations. Our computation analysis is twofold. We try to replace simple AI CPU operators and use the roofline model for complex AI core operators to categorize bottlenecks as computer-bound, memory-bound, or underutilized, providing target optimization guidance. Our communication analysis have two parts, synchronization and transmission. First, we analyze synchronization delay, which is the time spent waiting for the slowest worker, typically caused by slow computation or scheduling. Then we analyze the transmission itself to see if it's limited by physical bandwidth or more often underutilized due to issues like small package size. Finally, in the optimization stage, Hermes provides automated suggestion with an optimization tool, MSTT Advisor. It does this through a cost and optimization matching table built from our extensive experience. We have built a knowledge base from over 135 real-world industrial cases, which maps specific bottleneck costs to optimization strategies. As you can see from this table, CPU and computation bottlenecks are the most common issues we have encountered. So what are the key takeaways from our analysis? We have distilled them into 5 key lessons shown on this slide. First, on the host side, CPU scheduling bottlenecks are dominant, but surprisingly they are often overlooked. Then on the device side, we found that computation bottlenecks are mainly caused by resource underutilization. And for communication, a common trap is performance degradation caused by resource content when trying to overlap it with computation. At the physical network layer, the most common problem was actually simple hardware fault, like port flapping and link failures. Finally, for I/O, the most effective strategy is to minimize remote data access to reduce overhead. And with these lessons, we are able to systematically tackle complex optimization problems. Now let's see how this works in practice through some case studies. Our first case study is the 100 billion parameter PanGu-α model trained on 128 ASIN chips. Optimizing such a large model is an iterative process. Guided by Hermes, We achieved a remarkable 3.05 times speed up by successfully addressing computation, parallel, and communication bottleneck. We omit the detailed step-by-step process here, but interested readers can refer to paper for more details. Beyond just one large model, we also apply Hermes to optimize the deployment of various other models. As you can see in this table, our optimizations delivered significant results across different domains, including vision, NLP, and recommendation models. The total training speedups range from 1.08 times to as high as 5.34 times. The detailed analysis for each of these cases can be found in our paper. Another common challenge Hermes can solve is the performance fluctuation in long-run jobs. We observed this during a large-scale MOE model training on 9,000 cars, where Python's garbage collection was a primary cause. By increasing the garbage collection threshold and actively perform garbage collection during checkpoint saves, we significantly reduced this fluctuation and achieved a 1.05 times average throughput speedup. Finally, I will provide a conclusion. In conclusion, we have presented Hermes, a systematic optimization system that features lightweight profiling, hierarchical analysis, and automated guidance. We have also summarized key insights from 135 real-world industrial cases, providing valuable lessons for community. Our case study demonstrates that Hermes can effectively accelerate the training for a wide range of models on Ascend platforms. For future work, we plan to expand Hermes to support emerging paradigms like reinforced learning, enhance its ability to diagnose more complex bottlenecks, and integrate logs and even LLM-based agents for more automatic analysis. That's all, and thank you for your listening.